Hey, this is OXDF. Excuse my mess, we're still recovering from a plumbing incident here, but more importantly, today we're here to talk about scripting x64dbg with Python and the power that that's going to bring you. So in the 2024 Flare-On challenge, like 3 or 4 months ago, I had this challenge where I had this large buffer of shellcode, and it jumped around in the buffer and kept raising exceptions and then using error handling to jump back somewhere else. And the code was constantly changing itself, executing, re-obfuscating the code it just ran. It was a huge pain in the butt, really inefficient, but like made it really hard to debug. And I needed a way to log these commands as they were happening so I could see what was actually going on. And so x64 has a scripting language, and I started there, but I quickly ran into limitations that I couldn't overcome. And that's when I found x64dbgpython. It's a plugin for x64debug, and it allows me to write Python scripts that drive x64debug while also providing access to Python and like all that Python can do. I love Python, so that's my happy place, right? Today, we're going to look at the tool and how it works in the context of the Serpentine challenge from 2024 Flare-On. I'm not going to get totally into how to solve this challenge. I wish I had written a blog post about it when it was actually had just finished, but it was kind of burnt out and moving into the other CTFs of the season. So at least we'll get this video out. I'm focusing on not necessarily how to solve that challenge, but using it as an example for how we can script x64debug. So let's take a look. I'm going to start here on the page. So it's Elvis Blue x64dbgpython is the plugin we're going to need. And there's a note down here that anything past March 2023 release of x64debug, I'm also going to need this path plugin here. So I'm going to grab both of these from the releases. I've already done this, so we'll just go and check it out. If we come here and go to, I'm in my x64debug release x64 plugins directory, and you'll see here, in addition to Scilla, I've also got this path plugin as well as the x64dbgpython plugin. And so when I have those and I load this up, I'm going to have in the plugins here this x64dbgpython with the ability to run scripts, etc. So with that, how do we use it? So there's a couple example scripts. I can plugins x64 run script. I can also Alt F7. I'm going to start using that a lot to avoid lots of clicking, although there's still lots of clicking. And I grabbed a couple of the scripts out of their example on the GitHub. There's some examples. So we can try the HelloWorld script. You can see it down here at the very bottom in very small text. I don't know how to make that bigger. It says HelloWorld. More importantly, if we go over to the log, you'll see we've put HelloWorld here. Let's clear this and start. Cool. So now, same thing, Alt F7, Hello World, and boom, Hello World pops up right here and here. So we can try another more interesting one. I guess I could have Alt F7, but if we try the main module.info, and you see it printed out a whole bunch of information about the main module. Yeah, that's that. We can actually take a look at, let's see, where was my Explorer? Close that somehow. Desktop. Serpentine vid. Let's open this with code. Cool. So if we look at Hello World, it's going to be very simple. It just prints Hello World, just kind of like we expect. And we can just see the output went into the log window. So that's cool. This one, we've got a bunch of functions here, and basically it's going to call main module get main module info to get a main module object. And then it's going to pass that through a handful of different functions. You can see we reference the base address here. We use that to get the sections. We get the imports off of that, and we have an import list in front of each of those, and that is what shows up there. And so, again, we can start to, when you do x64debug, when you look through these examples, you're going to see there's different things you can import here, like modules, one of them, and then those have functions to get information off of it. So let's take a look. We'll go more in depth. I guess one more thing we can do if we want to just take a look. One other thing I found really useful when doing this is to have like a test.py. Is that closed? I don't know why I closed that already. Let's open that with code. And we come to test.py. It's like all commented out here. But the point of what I did was just have this thing available because the documentation for this is pretty sparse, at least at the time of when I was doing this. So if I was kind of like, oh, there's a register object, but what do I do with it? Cool. So I just open it up in my thing here and just do print dir of register. And now if we come here and Alt F7 test.py, Module not found tracer. That was not what I was expecting. Let's get rid of that for now. I'm not using it anyway. Come here, Alt F7, test.py, and boom. Now you've got all the different functions or attributes of the registry object, and you can say, oh, look, there's a get BP. So if I needed to get the BX or EBX or RBX, you can see those functions are all right here. Here's set RBX, etc. And so I can use those to figure out what I'm doing, as well as troubleshoot small pieces of code as I build out my bigger code. Because actually this tracer I'm going to build is actually going to have to run for 15, 20 minutes to actually dump the whole thing. And so I want to be able to develop little parts of it as I go. Let's take a look at the code itself. I'm going to do a little, this video is not really about the Serpentine challenge, but to show you what we're going to try to do, we really kind of need to understand it a little bit. So I'm going to just give a kind of an overview. If we start and run this to break, what the binary does is it actually has some TLS callbacks that run before the entry, and they allocate a buffer and decrypt some shellcode into it. And then that shellcode is like shellcode, and it's also full of like halt crashes, basically. And it uses these crashes along with error handling to just bounce around to different places in the buffer. And those places in the buffer are actually going to modify or self-modify. So before I get too far ahead of myself, let's go there. So we are currently, let's see, we run here. We're at this is the TLS callback 1. We run again. Oh, I've got some breakpoints already in place. Let me turn these off so we can. That looks reasonable. Oops, didn't mean to open. Let's start again. And so I've got a one-time on entry. That's what I wanted. So let's run here. We are now at the TLS callback 1 because we break there by default. Now you can see we hit this halt, and I think this is, yeah, we're just getting big text here. We're in the shellcode buffer here, and we're hitting a halt. And if we just try to like step over this, we just end up out here in, where even are we? Are we in NTDLL? So if we try to like run to user code, we're back at another halt. And so it's very frustrating to try to debug this. So what we need to do is figure out where is the point where it calls back. Well, so where is the point that it calls back into the buffer? And so we can actually cheat a little bit. In NTDLL, the error handling callback is right here. So if we turn that on and we run to here and we run, okay, we hit the halt, we run again. Now we're at the call RAX, and that is where we return into the code. And so we can actually step out or step in? Let's try step in. And now here we are. Now we're in the shellcode buffer. And I wanted to just show you one example of what this code does once it's here. Let's see, if we step into this and we step over, yeah. So if we look right here, we'll note the address. We'll go step forward a little bit here to right here. And so now it's going to take it's loading some value into EAX, and then it's going to take EAX and put it at 6CD4D49. Well, that's right here. So it's about to change the 4 bytes that are here. And so if I do this, you'll see this goes from being an OR AL to being completely different. So now we have a move some value into R11. And then as soon as I do that, look, it's going to put some other value back into that same spot. So it's going to run that, it's going to update that command, run that command, and then re-hide that command. So boom, now it's gone again. So it was there, it ran it, now it was not there, it unobfuscated it, it ran it, and it re-obfuscated it. So this, as I start to figure this out, what it tells me is like, oh, okay, I need something that just traces every command that's run in this shellcode. But that's gonna be really hard, and that's where I set up to write a script. So we're gonna start, again, we're not gonna write the whole script here, I'll go over my script at the end, but just to sort of get a feel for how we can develop in this, go back here and make ourselves a demo.py. And so we'll do from x64dbg, import module, debug, and memory. I think that's enough for us to start. We'll say if name equals __ main def main. Boom. Okay, and now what are we going to do? So the first thing we need to do, let's go ahead and do just kind of what we saw that in that example. We'll get the main module is equal to module dot get main module info, just like that. The next thing I want to do is I want to locate my address for that shellcode. And it's changing every time because it's the result of a virtual alloc call. So what we're going to do is we're going to say, I'm going to come up here. It's actually easier to do this as a function. We'll call get func address module name string. I could try to figure out what the typing of a module is here, but we're gonna let that go for now. And so we'll say import list is equal to module dot get imports. We saw that in the other one as well, like that. And then we just need to do, really what we just need to do is we need to find where that value is, where the name of the import is that is the one we pass in. So we'll say for item in import list if item dot name. And so again, I didn't know this right away, but this is where I use like a test dot, a test .py. So I would say I'd write this in here, and then I would just say, okay, import list 0 dir on that and see what it has. Oh, it has a name function. Perfect. Okay, so we can say if name equals name, and then we're just going to return. And again, this is something else I would do. Memory dot read word, because this thing is actually the pointer to the address, and it's item.iatva. And so now this will return us the address of a function. So we can say virtual alloc address equals get func address main module, comma, virtual alloc, alloc. Now we can say debug dot set breakpoint virtual alloc address. It'll be helpful. Usually this gets set by default, but just in case it gets cleared, it's nice to just have it by default. One of the things as we get going on debugging and running, knowing what breakpoints are set is really valuable. So we'll say set breakpoint. Oh, I think they're lowercase. Let's see, point main module dot entry. Make this a t. There we go. And let's give that a run. Let's see what happens here. So if we take this, we save that, we come over here, let's reset our binary, because it'd be cool. There might be a function, I don't know, maybe there is a way to do this. I didn't know a way to reset back to the beginning. So if you don't reset, it will run from wherever you are. So we want to make sure we reset. Okay, so we have that, and we'll run demo.py. And you'll see down here, it says breakpoint enabled. If we go to the log, both those breakpoints got enabled. So it enabled 2 breakpoints. We can go a little bit further here, and we can say, okay, so what if we do debug.run and see where we end up? So if we come back here, we will reset just to be sure. We'll F7 or demo, and boom, here we are. Where are we? We are in serpentine.exe. We're at the TLS callback. I think, if I remember, well, so we need to run through this. So let's come here, and we will debug.run, because it's only going to run commands when it regains focus. So after this run returns, that's when the next we'll do it twice, so we get there beyond it. Run that, and Alt 7 demo, and boom, here we are at virtual alloc. We're jumping to virtual alloc, and that's pretty cool. What do I want to do now? Well, from here, what I really want to do is step out. If I step out, now I'm at the return. Now I'm at the return value, the return from virtual alloc, and the buffer address is sitting here right here in RAX. So what we're going to do is go back over here. We can say debug.step out shellcode equals register. And again, that took some debugging / looking at the examples to figure this out. But we can do register dot register num.rax. That'll get us the address of shellcode, and we can say print. It's an f string shellcode buffer ox shellcode x. Boom. So let's run this again. Come here. We will reset. I will Alt F7. Open up the demo. Get to this return. Let's see. Let's go to my breakpoints here. Oops, no, not where I want to go. Log. Perfect. So shellcode buffer is 6AE000. We can come here and is it G? Nope, not G. Control G. Paste that in, and boom, here we are at the top of the shellcode buffer. It's all nulls right now because it hasn't filled in. But if we put a breakpoint right here and run, We are at the entry now, and boom, here we are at the top of it. It has changed. So we have identified, now we've got code that finds us the shellcode buffer and it doesn't currently put a breakpoint there, but it could. And so we can start to build off of that. And that's where we can start to say, okay, well, what if I'm doing this manually, what would I do next? Well, I'd run to that, I'd want to run to the EAX, that return EAX thing. Well, how do I find that? And I'd start to walk through the steps of that. I think we're getting far enough in the video that it's probably not worth me showing those next steps, but rather, I think at this point, what I'll probably do is just open up this and walk through, here's my tracer program. Because this is the program I used to solve it. I'll try to put it on GitHub somewhere or GitLab so that it's available. But basically, okay, so this is going to look a lot like what we just did before. So we're going to get virtual alloc. We're going to set these breakpoints. I don't quite remember why I disabled this breakpoint. Maybe that's just the entry break. Oh, I bet that's the maybe that's the TLS callback, and I actually just didn't want to have two runs because I only had one run here. So two ways to handle that, right? You can just disable that breakpoint, or you could just run twice. Then I'm going to go ahead and get the shellcode address, print that out. Next thing I did was actually ran to into the buffer and ran far enough that it stopped, and then put a breakpoint 98 bytes into the shellcode. And what I can actually do here is find the address equivalent. Basically, I can find wherever that RAX, the call RAX value that steps back into it. I think I showed this at the beginning. And I can find this thing, get that address, and put a breakpoint there. And having that breakpoint there is what allows me, if you remember, that's how I was able to then I could step in and actually start to run things. So what I do here, now I come into a loop, and I'm going to say, I'm going to get RIP, and I'm going to check. If RIP, I have my own little in-module function. Let's see, what is that up here? It's pretty simple. Pass in a module, and then if the address is greater than the base and less than the base plus the size, then I'm in the module. So I can basically check and say, if I'm in the module or in the shellcode, then I want to log. What I don't want to log is all the other stuff. So if I'm not in module or shellcode, then I'm just going to add one. I'm going to run until I get to the breakpoint and step back in and then check where I am. And if that puts me in the module or shellcode, I start logging. Otherwise, I just run again. Then otherwise, I'm going to start keeping these frames. And a frame is a snapshot. I'll show that in a second. And I'm going to append it. I'm going to print some stuff. Let's ignore this all for 1 second. And then I'm going to debug step in. So I'm going to debug, take a step and go again. And so as long as I'm in this stuff, I'm going to step a time, and once I do that, I'll come down here and loop, and now I'm back at the top, and I'm going to check and see where I am. And so as long as I'm stepping and staying in, then I'm going to keep logging. And as soon as I get out, I'm going to run until I get back in. So we have to talk about snapshots. And so this part right here, basically the way this challenge ended up being set up is there was, I don't remember, was it 16 or 32 blocks of stuff, and each one checked a small amount of the flag. And if the flag input at the command line was not correct at each check, it would just bail out. And so what I eventually decided to do was identify kind of this place where, after a lot of analysis of these logs, I could identify what those compare instructions looked like. And that is like the jump to going to exit. So if I'm going to move this into a certain place, and that is the call to exit, then I'm going to do this other stuff to basically change and say, oh, keep going, actually. Just, yeah, sure, you passed. And so I patch the binary on the fly and keep running. And that allows me to get the whole thing. Let's see, snapshot real quick up here. I just created a little class right here, and it is literally, when I create a snapshot off of a frame, I'm going to capture all of these different registers. I'm also going to get the assembly instruction at RIP, as well as the mem value of the operands. So self.instruction, what is instruction is, oh, right here. I get the assembly, and then off the instruction there, I'm going to get the mem value, which is a function in here somewhere, I think. Yeah, so here's a function that does, this really should be a part of the class, but okay, maybe not, maybe not. Anyway, so get the different mem values based on, and that's going to have to check and see based on the instruction, like, is it a pointer, or is it an offset, what is it? So it tries to load the right thing and log it. But in the end, what I'm going to get is, let's see, oh, I didn't grab any of these. Let me go real quick over here. Flare on 2024, Serpentine. These logs, I'm not going to load the giant one when it actually fully worked, but like the first one I ever got, it's not too big. And it's just a bunch of, so frame 0, RIP, here's all the registers, here's the operands, etc. And you can see the instruction and all this stuff. And it's just a ton of this data. And my whole point here was just to log a ton of data. Oh, I don't think I showed the end. So I get down here, and when I finally hit a place where this can't work anymore, like really because the program stopped, I get an exception and it prints and it breaks. And then I'm going to show how many frames I got, and I'm going to open and write all of this data in JSON to a file. And so now I've got all this stuff that I have pulled out, and I can write other Python scripts to parse and figure out what's going on and evaluate. So I'm not going to go into that because that's different. That's solving the challenge, which was a really interesting challenge. I wish I remembered how to do it. Maybe I'll have to get a write-up going at some point. But for now, the whole point is really just to talk about this really cool ability to automate x64 debug. I'm going to call it there. Thanks for hanging out with me today. I hope you enjoyed this. Thank you for staying to the end. It's a great way to support my videos. And I'll talk to you next time. Bye.